Hello, I'm Libor Barto, and I'm presenting a joint work with Marcin, Kozik, Johnson Tan, and Valeriote on sensitive instances of the constraint satisfaction problem. Constraint satisfaction problem, or CSP for short, is a decision problem whose instance is a list of local constraints on possible values of variables, and the task is to decide whether there is an assignment that simultaneously satisfies all the constraints. A natural idea for solving a CSP is to look for implied constraints. The k+1 consistency algorithm simply derives the strongest constraints on k variables that can be derived by considering k+1 variables at a time. This is a polynomial algorithm for fixed k, and the question is how well it performs on a class of instances. It can perform so-so, by which I mean that if no contradiction is derived, then a solution always exists. I call it so-so, but it is actually quite good, because then we can use this algorithm to decide in polynomial time every instance within the class. The algorithm can perform way better, I call it great, and this means that in the new instance every partial solution on k or more variables extends to a solution. This also means that we can find a solution by greedily assigning values to variables. Somewhere in the middle of so-so and great is good, by which I mean that every partial solution on k variables can be extended to a solution. In other words, every sharpening of a constraint in the new instance invalidates some solution. Such instances we call sensitive. In more detail, an instance of the CSP is a list of constraints of the form Rx, where X is a list of variables called the scope, and R is a relation on a fixed domain of appropriate arity. Here is an example. An instance may look like this, where R is a binary relation on the domain 0, 1, 2, and S is a ternary relation on the same domain. A solution to such an instance is a mapping assigning domain elements to variables that satisfies all the constraints. For example, if we evaluate x1 and x2, we get a pair which must be in the relation R. A partial solution is a partial mapping satisfying the same properties. The central notion is that of sensitive instance. An instance is sensitive if every sharpening of a constraint invalidates some solution. For example, if we replace R with a smaller relation in here, we lose some solution of this instance. Now about the k+1 consistency algorithm in more detail. So let's fix some k, and for simplicity we assume that all the constraint relations have arity at most k. Actually, I will not describe any algorithm, I will rather say what we want to achieve. So a k+1 consistency algorithm produces a so-called k+1 instance that satisfies two properties. First, every k-element set of variables is constrained by a single constraint, and there are no other constraints. And second, whenever I take a partial solution on k variables, I can extend it to any additional variable. Moreover, we want the algorithm to work in polynomial time, and we don't want to change the set of solutions. It's quite easy to come up with an algorithm that achieves all these goals, and we will call any such algorithm the k+1 consistency algorithm. Let's now look at a concrete instance and see what a 2-3 algorithm can do. The instance has domain 0, 1 and 5 constraints, which are drawn on the figure. The variables are x1, x2, x3 and x4, and the constraints are drawn by lines. So for example, R is the disequality relation on 0, 1. So we have two possible evaluations, x1, x2 goes to 1, 0, or x1, x2 goes to 0, 1. Now the first condition we want is that every pair of variables is constrained. This is achieved simply by introducing a dummy constraint between x2 and x4, like this. So all the four pairs will be possible evaluations. Now the second condition says that any consistent evaluation on two variables extends to any other variable. Let us consider the evaluation x1 goes to 1 and x3 goes to 1. And let's look at the additional variable x4. We see that evaluating x4 to 1, we get a partial solution because we satisfy all the constraints, so this is fine. But when we look at the same partial evaluation and the variable x2, we have a problem because if we send x2 to 0, we falsify the constraint between x2 and x3. And when we send it to 1, we falsify the constraint between x1 and x2. So now we can say that this partial evaluation is never part of a solution and we remove it. So this we do for every edge we see here until it stabilizes, and when it stabilizes we get a 2-3 instance. In this example, actually the instance will become empty, so our consistency algorithm is perfect. Recall that the question is how well the k+1 consistency algorithm performs on classes of instances, and the classes of instances we consider are parameterized by templates. A template may be a relational structure, which is a set together with a set of relations, or an algebra, which is a set together with a set of operations. The CSP over a relational structure A is the class of instances where every constraint relation is coming from A. By choosing various A's, we get various well-known computational problems, such as 3-SAT or solving systems of linear equations over ZP, or Horn 3-SAT or 2-SAT. The CSP over an algebra A is the class of instances where each constraint relation must be compatible with every operation in A. Compatible here means that the operation applied to tuples in a relation gives a tuple in a relation. Here are a few examples. By choosing the algebra like this, so the operation is ternary addition modulo 2, we get a problem which is very close to solving system of linear equations in Z2. By choosing the minimum operation on the set 0, 1, we get a problem which is very close to Horn-SAT, and by choosing the ternary majority operation on 0, 1, we get a problem very close to 2-SAT. We are almost ready to state the main result. For that we need two more definitions. An operation T is called idempotent if T applied to a unanimous tuple gives the unanimous value. T is called a near unanimity operation of arity M, or NUM for short, if T applied to a near unanimous tuple, with one exception allowed, gives the near unanimous value. Now the main results says the following. Let K be an integer and A a finite idempotent algebra, then the following are equivalent. First, A has a near unanimity operation of arity k plus 2. Second, every k plus 1 instance of the CSP over A square is sensitive. There are several annoying assumptions here, namely the idempotency and the square in the second item, but they are provably necessary for the implication 2 to 1. However, this implication is mostly interesting for universal algebraic consequences of our main result, and for the other implication, which is more interesting for us now, they are not necessary. So it is true that if A is a finite algebra with a near unanimity operation of arity k plus 2, then every k plus 1 instance of CSP over A is sensitive. We also have a more general version of this result for infinite idempotent algebras, where we need to replace NU by local NUs. Now I can give some answers to the questions from the beginning, namely, how good is the k plus 1 consistency algorithm for the CSP over a relational structure A. So let's fix some k, and let's consider a structure A whose all relations have arity at most k. It follows from a known result that if A has a compatible near unanimity operation of any arity, then the algorithm performs so-so, meaning for any instance of the CSP over A, if the associated k plus 1 instance is non-trivial, then we have a solution. A way older result, coming from essentially 77, implies that if A has a compatible near unanimity operation of arity k plus 1, then the algorithm is great, meaning for any instance of CSP over A, in the associated k plus 1 instance, every partial solution on at least k variables extends to a solution. Our result implies the following. If A has a compatible near unanimity operation of arity k plus 2, then the algorithm is good, meaning for any instance of the CSP over A, the associated k plus 1 instance is sensitive. In other words, in the associated k plus 1 instance, every partial solution on k variables extends to a solution. Let me note that compatible near unanimity operation of smaller arity implies a compatible near unanimity operation of higher arity. So the condition for greatness is indeed stronger than the condition for goodness, and which is stronger than condition for so-so-ness, so it makes sense. Let me add two more remarks. The great part has a converse, namely, if we have a template A such that the algorithm performs great, then necessarily A must have a compatible near unanimity operation of arity k plus 1. The condition for so-so-ness can be weakened, and then we also have a matching converse. We do not have converse result to the good part, unfortunately. Let's look at some examples of computational problems and see how good they are. The problem of solving systems of linear equations over ZP is, of course, solvable in polynomial time, but the k-consistency algorithm is not good enough. That is, for no k, the k-consistency algorithm can correctly decide every instance of this problem. For Horn 3-SAT, the K-consistency algorithm can correctly decide every instance, but not in a sensitive way. 2-SAT is great. And the last example is a structure whose CSP is good but not great. The CSP over the structure is a fragment of 0-1 linear programming. A few remarks about the proof of the main result. For the backward direction, which I didn't talk about that much, we carefully choose several kk+1 instances of the CSP over A square, and they give us some very local near unanimity operations. And these then can be assembled to a global NU using a result of Horowitz. The proof for the forward direction is quite complicated at the moment. The main tool is a new loop lemma, which improves a loop lemma of Olszak. In general, a loop lemma is a theorem of the form: if a digraph satisfies certain structural assumptions and certain algebraic assumptions, then it necessarily contains a self-loop. We proved two new loop lemmata. One of them goes as follows. If a digraph contains a directed closed walk and absorbs all the self-loops, then it necessarily has a self-loop. I do not explain what absorption here means and how the theorem is applied, and I need to refer to the paper for details. Anyway, we believe that the two new loop lemmata may be of independent interest. To summarize, let's look at the main message of this talk from a bit different perspective. So let A be a relational structure that has only unary and binary relations, and let's assume it's compatible with a near unanimity operation of arity k+2. Then we have the following facts. If we enforce 2-3 consistency and we find no contradiction, then there exists a solution. If we enforce a lot more, the k+1 consistency, then every partial solution on k variables extends to a solution. This is the sensitivity property. If we enforce even slightly more, namely the k+1, k+2 consistency, then every partial solution on at least k variables extends to a solution. To wrap up, I have 4 questions. There is a gap between 2-3 and k+1, and the question is whether there is some natural condition or natural conditions that can be placed in between. The second question is that the first item and the third item have characterizations by means of compatible operations. We do not have such a characterization for sensitivity. The third question, again, the first and the third item have natural versions for relations of higher arity. And again, we do not have such a version for sensitivity. And finally, the characterization of the third item has a generalization to a class of infinite domain structures, namely the omega categorical ones, by means of so-called oligopotent quasi-NUs. Here, oligopotent is a generalization of idempotent, and quasi-NUs are generalizations of NUs. The question is it possible to generalize our result to to this setting. So this is all I have to say, and thank you for listening.